Good morning, everybody. The fact that you've actually shown up this morning, despite what was apparently a late night last night, shows how committed all of you are to listening to Professor Bruce Hansen. My name is Meenakshi. I'm on the faculty here at the Delhi School of Economics. So Professor Hansen is the Mary Claire Askenberger Phipps, if I've got that right, endowed chair at the University of Wisconsin. He also happens to be the Havelmore, name more familiar to most of us, Havelmore Professor of Economics. His research interests, even within econometrics, are really astonishingly diverse. I think in the 1990s, a lot of his work was on time series. He then has significant contributions in the area of non-parametric econometrics. Of course, the more recent work is what is going to be talked about in today's lecture. So I think every third paper, it seems, gets published in Econometrica. So that itself is mind-blowing. And in fact, I think it's his Econometrica paper that will be the subject of the third lecture today. What he's going to talk to us about is on clustering and clustered regressions and variance estimation. I think most of us who do applied econometrics, this is a question that we often struggle with. What level to cluster? What implications does it have, whether you cluster at one level or another level? And I wouldn't hesitate to say that this is a problem that most of us in this room face if we've done actually some applied work. So I think he's going to enlighten us about those in the next couple of lectures. But before I hand over to him, I also wanted to mention something that probably he's not aware of. When the pandemic hit and most of us were sort of forced to move to online teaching, and at a time when I was actually teaching the econometrics course here at the Delhi School of Economics, we'd been relying on textbooks such as those I had been relying on a textbook by William Green. And so it was really difficult to figure out how to provide teaching materials because there were no online versions of the text. So actually, I switched to Bruce Hansen's text. At that time, it was freely downloadable. There were sort of two versions of it. And I, of course, used the econometrics text, but I would often refer to the earlier version, students to the earlier version if they needed brushing up on basic concepts in probability and statistics. And we used to refer to them jokingly as Baby Hansen and Papa Hansen. I'm not sure if he's familiar with those two terms, but I thought I would mention it. So it turned out to be a real lifesaver, not just for me, but for I think many of us in the community who were faced with the prospect of teaching econometrics when students, for us who lived in all parts of India, often with poor internet connectivity, didn't have access to a library where they could source a good textbook. So I wanted to express my appreciation for how valuable that was for us. And I also recommend it's now available for purchase. If you don't mind my putting in a plug for those two books, I think it's really a worthwhile investment. So with that, I'll hand it over to him.
Well, thank you. Thank you. Appreciate that. And the books you're referring to, and I guess everyone's familiar with this concept, came out this summer with Princeton, and the economics editor who I worked with on this, when I described said, here's two books, publish them, take it or leave it. We talked about it for a bit, and he said, well, you know, this first one's going to get known as Baby Hansen. So if you're thinking that, it's not. It's not. It's probably how general that was, but yeah, we'll do that kind of thing. So the other thing I would like to mention about that is just my goal of going with the publisher finally, after having it online from different iterations all these years, was to make it kind of a more solid professional piece rather than people would refer to it as notes or something, and rather when it's cited. It wasn't trying to squeeze money out of anybody. So and it is kind of annoying that there's not a PDF version available, but if you go to Amazon, you can buy a Kindle version for a reduced price. It's not that much reduced, but for a reduced price. A Kindle version is a bit annoying because it's not the same thing as PDF, but there are PDF converters. I have a description on my webpage of the one I use to make my own PDF copy. And so legally, you only can use that for your own self. But once you have a PDF copy and have unlocked it by the PDF converter, what you do that is up to you. So I'm not going to legally post it because my publisher won't like me for that. But so you understand what I'm saying. I'm going to start with trying to understand the concept. Is it not quite right? Should you think it's her? Okay, that was too much, but yeah. Some work I've been doing. I've been doing some work for a while now on clustering, but not really the question of what level to cluster. That's a question I haven't really wrestled with, but of how to do variance estimation. So I think, and by the way, I have a lot of slides. I don't know what I'll get through or not, but feel free to interrupt me and ask questions because I want to make sure everyone's understanding at the same level. My big thing I like to think about is variance estimation, standard errors, because and the nuts and bolts of applied econometrics, what people do is they present regression results and standard errors. That's what people do, okay? I know there's other things we do. People say, oh, I want to do a test of this, test of that, but bottom line is standard errors are the thing which just distinguish us from calibrationists. And so that is the key here. And standard errors, when you have clustering and heterogeneity, is more complicated. Clustering right now is the most common sampling structure that you see in economics. And I don't know if this is a broad statement in all journals, but if I peruse top journals, it is undoubtedly the case. Because I've done things just going through and looking through every single paper in the American Economic Review in a particular issue, or I've done that for the last few years. And roughly third to a half of the papers have clustering right now. And then there's another quarter that are time series, and then there's some theory papers. But the dominant issue is clustering. Now, there's different types of clustering that you may see, but the most common clustering structure that people use for forming their standard errors is the type of clustering structure I'll talk about now. In the second talk, I'm going to talk about another form of clustering that's also extremely common, multi-way clustering as well. But the standard clustering structure is that you have a large number of observations, I'll call that N, and then you have clusters. Now, many times in development, people will cluster on the basis of a village. So you probably are familiar with that kind of idea, clustering observations within villages. I'll use the notation G to denote the number of clusters, the number of villages, the number of schools. Or if this is a panel data, it might be the number of individuals or firms. The standard assumption people will make, whether it's right or not is a different question, but the standard assumption we make is that observations are independent across clusters, but then within each cluster, they are correlated. Now, the old order literature, people would talk about, let's make a model for how people are clustered within the cluster. And in certain panel data structures, that would make sense. But then as things got more complicated, as we think about villages, it's really hard to understand what would be the correlation structure within a village. And so people said, let's be agnostic. It could be anything. It could be everyone's all the same. It could be everyone's all independent. It could be there's one village leader. And so the unstructured correlation structure within the cluster. Now, there is this issue about what level to cluster, and I think it's a really fundamental issue, and I feel that a lot of the discussion in the applied literature is wrong, just because it's kind of made up. And but I'm really not going to address it too much today. But the some just choices that you could have is family, firm, school, classroom, village, district, state. So there's some sort of agglomeration that you're going to use. And I think the best way to really think about this is to think about the economics, about who interacts with who and why they might be clustered dependent. And a common example, of course, is panel regression. You observe an individual over time, and then that you have the obvious thing is clustering at the level of the individual or firm. And also it should be useful to recognize that standard regression, we might call it heteroscedastic regression, but it's the independent sampling framework, is a special case where each cluster has one observation. Yes.
So about the clustering level of when would you think maybe you'll get to that so when you have a panel setup where the unit of observation is, let's say, the firm, when would you prefer to cluster at the firm level rather than actually explore the dynamics in a dynamic panel data setting? It almost seems to me that either you use dynamic panels or you just cluster. It doesn't seem like,
yeah. Well, you should do both.
Okay.
So if you do dynamic panels, they are also clustered at the level of the firm. So, but an interesting question there, I think, is when should you model the dynamics? Because you could do a regression where you regress some y on some x with no dynamics, or you could model the dynamics. And my general view is that you should do whatever's right. What does it mean by what is right? Is that if there truly is dynamics, you'd need to model that. And in firm level data, it's hard to believe that there's not dynamics. So I strongly believe part of the challenge there, frankly, is that dynamic panels are more complicated to estimate and deal with. They have a lot of extra problems, which I'm not going to deal with per se today. But even once you're there, you still have to deal with the clustering for there. But yeah, then the question might be is, well, how much dynamics? Should you have one leg, 3 legs, etc.? And I think the main problem is limitation of the identification and data. Basically, one leg is typically all that you can deal with before you get into identification failure. So like when a student comes to me and they say I'm doing this panel regression, I'm thinking, what should I do? And maybe what should I do? But give me some advice. Will you pass me? I often will say, now add a dynamic specification because I bet you'll find it's relevant. So even though this is not the main purpose of the talk, I do want to mention that an important practical issue is really what level should you be clustering. And my theory that I'm going to be talking about today assumes that the researcher knows the level of clustering, and so that the clusters are truly independent. Now, so that means that this is a high level of knowledge, and that's not realistic. You really don't know. In practice, you're going to have to pick. So I'm ignoring that. And now it's useful to think about what that implies in terms of most often choices have a trade-off. So what are the trade-offs that are, just to state the obvious, is that if you pick the level of clustering at too fine a level, an extreme example would be one individual per cluster, or maybe clustering at the level of a family, then between cluster correlation will be missed. You're probably missing correlations between the clusters. So you say, okay, I want to not have any kind of bias due to missed correlations, so I'm going to aggregate. I'm going to cluster at the level of a bigger group, not the level of family, but at a neighborhood. No, not the neighborhood, but no, not the neighborhood, the village, but the district. Why country, etc. Well, if you do it at too coarse a level, you're going to have is only a small number of clusters, and then variance estimation will be imprecise. Confidence intervals will become bloated, and your inference will become inaccurate. One way to think about this is that variance estimation, the precision of variance estimation is based on the number of clusters, G. I've noticed that many people, when they do cluster regression, do not even tell the audience the number of clusters. That's a huge mistake. You need to say, I have 12 clusters. Because if you say you have 12 clusters, it's like saying you have 12 observations. I mean, that's nutty. No one will report a regression and send it to a major journal with only 12 observations. So you need to have many, and using American data, cluster the level of the state, and we have 50 odd units. So that's 50 observations for variance estimation. That's fairly minimal, but that's not too uncommon in application. But you should have, but this is the trade-off. So what's my advice, if I don't really know anything here? It's that pick your clustering level so that you can reasonably argue that the clusters are independent or uncorrelated, but also that you have a sufficient number of clusters that you can apply large sample approximations and estimate the variances. And also so that the sample is not dominated by one or two clusters. And that's going to be the problem I'm going to be talking about today. Really, this is the problem I'm going to focus on, is what happens when you have one or two clusters dominate the sample. Having one or two clusters dominate the sample is the same problem mathematically as in regression, where you have one or two observations which dominate the sample. Extreme observations, outliers. So, and this may be difficult to avoid if you have, in American data, California in your data, and you cluster at the state level, because California has, guess what? That's where everybody lives. So if you have sometimes the clustering is given to you, you really don't have a choice, and you'll find that there's two clusters that have 50% of the observations, and it's something to be worried about. So these are the trade-offs. So this again is the summary I just said. So let's get on and talk about the notation and the math. We have observations using the standard notation. Y is the left-hand side, X is the right-hand side. And then we're going to have subscripts I and G. I denotes the individual, G denotes the cluster. So G denotes the village, and then I is the person within the village. Typically, I will use the notation that I runs from N1 through N sub G. N sub G is the number of individuals in the village. So the Gth village has NG individuals. The villages range from 1 through G. X can be a vector. I'm going to be focusing on scalar dependent variables. An important thing that's often recognized by early theory, and when people kind of teach this, because it's harder from the notation, is that the number of observations per cluster is heterogeneous. There's no reason why the number of individuals per family is going to be the same, or the number of families per village. The cases where you may not have heterogeneity in NG is firm level data, where you have a kind of firm panel. You observe firms over 40 years, and you have 500 firms or something. But in other cases, we're going to see heterogeneity in cluster sizes. And as I mentioned before, classical regression, number of observations per cluster is 1. Just again, fixed notation is that I'm going to be looking at regression models, linear regression model. So y is equal to x transpose beta plus e. Simplest way model to think about is projection. So x and e are uncorrelated. You can also, it's useful to use notation for a full sample and a cluster level. Full sample, just stack all the y's, stack all the x's. And that's mostly useful just so I have the x prime x is pretty easy, but beta hat is you sum over clusters, sum over individuals when they cluster, and that type of notation, just a fixed notation. And so what are we doing? We're summing over clusters and summing over observations within each cluster. And one of the things you note is that the clustering itself does not affect estimation. It's the same estimator. What does it matter for? Dependence, and therefore variance estimation. It's also useful to use cluster level notation. So what we do is we stack up the data within each cluster. These are the observations for a village. I go to the village, I take all the observations, and I call that y sub g. And so in my data set, I just have all my Ys, and these are village 1, these are village 2, these are village 3, etc. And similarly for the X's, I have regressors. These are for the different individuals within the village, and I stack them all up into a big X matrix, and the same thing for the error term. And then I have a model written at the level of the cluster. Y sub g is X sub g times beta plus E. So this is a vector. This is a matrix. That's a coefficient vector. And the reason why this is useful is that for variance estimation, things are really done at the cluster level. So it's really the same thing as our individual level model, but it's different notation. And then using that notation, we can talk about the least squares estimator as the sum over clusters. So I'm averaging over villages of within cluster sums. So the X transpose X is the sum of the squared X's within a village. X transpose Y is the sum of the cross products within a village.
The last formula that you wrote up.
Yeah, so it's the same thing, but now I've moved from either full sample notation or individual level notation to cluster level notation. One of the reasons why I think this is useful to kind of think about is that oftentimes we think about doing inference or anything else at the cluster level, is it averages at the cluster level or sums? These are sums. This is sums of sums, sums of sums. And so the reason why heterogeneity and cluster sizes matter is because we're summing up sums. And when you take sums of different sum lengths, the big sums, that is the big clusters, dominate. So if you have one cluster with one observation and another cluster with 5,000 observations, the one with 5,000 observations will get all the weight. What are the typical assumptions that one makes in this kind of model? Well, so that's again the model at the cluster level. Well, what first is that the error has zero mean. Now this gets to the, I'm going to be ignoring conditioning on the X's in terms of explicit notation. So everything here is conditional on X effectively. And the way I've written this down here excludes the dynamic panel setting. So I'm not looking for, in some of the notation and theory I'm looking at today at dynamic panels, you'd have to use a different focus, but a lot of the same issues apply. But this is, the errors are zero mean. And what is EG/EH for G not equal to H? This is the one village. This is a different village. Their errors are uncorrelated. That's a standard assumption. It may not be true in practice, but it's what we use to derive the theory. But within a cluster, the covariance matrix for the Gth error is some matrix. So if I look within a village, I have, say, 100 observations of families within a village. The errors within that village have some covariance matrix. It may be they're independent. Maybe this is some sort of decision that people are making, the number of coconuts they buy or something. And it might be that those decisions are independent across families within the cluster, or maybe within the village, or maybe they're all the same. Maybe everyone does exactly the same thing. So this is the covariance structure. It could be all over the place. Yes.
In that formula. The hat, there is no, for variance, it might have implications, but in this, there is no dominancy, right? Because it's a sum of sums.
Yeah, that's right.
Okay, thank you.
Yeah. It's not a problem. It's just kind of realizing what the notation means and what's going on here.
Fixed effect.
We could. So one of the things here, I'll talk about fixed effects in a moment. So I'll get back to that, I guess. But in general, what the literature in econometrics, since the work of Manuel Ariano and others in the late 1980s, have said, let's allow for arbitrary correlation. We don't want to model something which is unmodelable. So within the cluster, observations are allowed to be uncorrelated or fully correlated. The sigma can also be a function of the regressors. So you can think of that as conditional heteroscedasticity. It might be that the village errors are more variable in households or villages that are wealthier or than in villages that are less wealthy. So if you thought of wealth as being one of the regressors or something, this might vary. But it also can be a function of the cluster. It might just simply be that these clusters have more variability than those clusters. It could be that these clusters have more within cluster correlation. It could be that one village is dominated by a village elder who really decides everything for the village. It might be the other does their own thing. That's unconditional heteroscedasticity. These are the type of things, reasons why you want sigma to be completely flexible is that there's really no reason typically to think that the same correlation structure is going to be in every single cluster, right? And so I give these descriptions here as choices could be correlated due to these things like kinship relationships, social relationships, economic relationships. And these are just very specific to that individual setting and will be different across different villages. Yes.
Going back to Meenakshi's question. So unless there is really compelling reasons for you to believe in a certain dynamics, isn't this a better structure than I'm arguing for not modeling the dynamics? Unless there's very compelling
Exactly.
reason. Yes.
Yeah, I just, that's exactly the point. I think that it's difficult to, we don't want to model the structure. Oh, I see, you're talking about the dynamics.
Yes.
Yeah, so that gets back to the whole thing about whether or not the coefficients in models are, can you even think about coefficients in models as being common across units? So why should the same betas be for village A and village B? So at some level we need to, I don't know. Yeah, because if the betas are the same, why not the dynamic coefficients? So it's a model with, when you model the dynamics, you are assuming that the dynamics are the same across villages. And so that is a potential weakness. Yeah. Truth is that the real world has heterogeneity, and it's hard to know how much. Yeah, it's a good argument. So one way of thinking about something which you may be familiar with in other contexts is that classical regression is when you have one observation per cluster. You might use this notation, and in that case, the error variance structure is just a unknown heteroscedasticity, which could be conditional on x's, it could be unconditional, and that the standard model we use thinks about the variances being unstructured. There's no reason to think that the variances are all the same. And it's the cluster regression context is very much analogous of thinking that the sigma, capital sigma, varies across clusters. And so this heteroscedastic regression is a special case. The question came up about fixed effects. Well, how does this relate to fixed effects? And the answer is that when I look at papers that do work with clustering, I think most use fixed effects, but not all. And so, well, why would you, or why wouldn't you, and what's the effect? Well, the standard fixed effect model is simply starting with the baseline notation, add a individual error u. So you want to think about this at the beginning as a model, and it's an individual effect, something that's common for an individual. That individual might be a family or some other agent. Over time, if we're thinking about this varying over time for a given individual, or some sort of commonality within a village, so I is denoted. I have bad notation here. This was meant to be subscript G. The notation should be U subscript G. Is that the fixed effect is common to the cluster, and so that U sub I is read it as U sub G. So the individual effect is a cluster level effect. And when we talk about it being a fixed effect, what you mean is that it's potentially not just that there's a random effect at the level of the village, but it might be correlated with our regressors, so that there might be villages that eat more coconuts than other villages, but that might be correlated with the fact that they live in a particular region, and that region happens to be wealthier or not wealthy or something else. And so there's reasons that we think that these things in general could be correlated. We call that the fixed effect assumption. And how do we typically estimate this model? Is we take group means and subtract them to get the within transformed model, or we get rid of the fixed effect. So the fixed effect is gone. Once you've made this transformation, we're back in the same notation we had before. So that is, instead of calling it y, now we have y dot. And so the model talked about before about cluster level data could have been within transformed data. So everything applies to fixed effects just after the within transformation. So why would you use one or another? It's really the question about whether or not you think there is this fixed effect. And if the model should have a fixed effect, then use it. What's the downside of using fixed effects is that you can't estimate coefficients which are on regressors that are common across all individuals in a cluster. So if you have treatment at the level of a cluster, then you cannot estimate a coefficient if you use a fixed effect transformation, if you do within transformation. And it's a limitation of within estimator. So I'm going to be talking about variance estimation. So to think about that, we want to think about, well, is the estimator biased or unbiased, and what's the variance? Well, pretty trivially, actually, I shouldn't use the word trivially. My daughter said when she was in college, a math professor kept saying that this result's trivial and result's trivial, and it made her feel very stupid. And so I should not say that, right? Because nothing is trivial, everything is deep. A deep result is that the estimator is unbiased under the assumptions, but it's a fairly standard thing which you should be familiar with from standard econometrics notation. Now the covariance matrix is a little bit more tricky, but given the cluster notation, it's not that tricky. That is, beta hat minus beta is this, ignoring the expectation, it's just everything up to x transpose times E. And so given the independence across clusters, the variance of this random variable will simply be x prime x inverse on the outside. And in the middle, you have the variance of the middle part. But if you have independence across clusters, the variance of the sum is the sum of the variances. So the sum of the variance of x transpose E, but that is just x transpose variance of E times x. So you just have this formula come out very simply using the cluster level notation. So this is the variance of the least squares estimator. We know this, we know that, we know that. What I don't know is the variance at the level of the cluster. So a standard error is the square root of an estimate of V. And so for standard errors, of course, what you want to do is compute this object. Now, what is, maybe about 10 years ago, people started, it was probably a little bit longer than that, clustering became ubiquitous in econometrics. And sometimes people would say, my standard errors are computed by clustering. And then early on, people would say, well, what do you mean? What do you do? And they said, I use the cluster command in Stata. So that was the answer. That meant that's what the researcher knew. So that is still probably the case. But what is it that you do? Okay, so let's talk about it. Well, let's drop out of clustering for the moment and go back to something you should be familiar with, which is variance estimation without clustering. So now the notation has no subscript G's. Take residuals, least squares residuals, and what you're probably were taught at one point is that the standard estimator is the so-called a white estimator, or sometimes people call it Eicher-Huber-Wright, or some combination, is this formula where you sum across the squared x's with the squared residuals. In fact, nobody uses that formula, despite the fact that you're told that is the way things are done. When the fact is that people use this. Why? Because this is what is programmed in Stata. again, what is done, and in R and other places. This is the standard formula. So this formula here is, James McKinnon came up with the names calling this HC0 and HC1, and I'll talk about HC2 and 3 in a moment. But what's the difference is this degree of freedom correction. Now, someone was asking me yesterday, what is the meaning of degree of freedom? And I was saying it's a mushy concept, but it is simply the number of observations divided by correcting for the number of estimated parameters here. Where does this come from? It comes from a paper due to Hinckley, and it's not particularly well justified. So this is what's programmed, but there's no particular reason for it other than it kind of feels like it does the right thing. It is somewhat the justification. But this is when you do regression with the robust or R option in Stata, this is what is computed.
Just makes it say that if any start,
Yeah, well, except if you do fixed effects. With fixed effects, K is includes a number of fixed effects. Yeah. So it goes proportionally with the number of clusters. So if you have fixed effects, this K here includes a number of clusters. So in that case, it can make it in principle can make a difference depending. But in most applications where you have reasonably large N and K is reasonably small, of course, this isn't going to matter. There's also what we're going to, I'll be focusing on why you should not be using HC1, but talking about why you should use HC2 at 3, but we also have to jump over HC2. What's HC2 is this idea here, which is instead of making this degree of freedom correction, you take the square residuals and divide by 1 minus the leverage point. What's the leverage point? It's these diagonal elements of the so-called hat matrix. It's these quantities. They're effectively a normalized length of the regressor. That look like a magical form of where does that all come from? Well, it comes from the fact that under the assumption that the errors of the model are homoscedastic, then the expectation of the squared residual is the true variance times this. So if I divide by this, I get a normalized squared residual, which is homoscedastic. Another way of thinking about it is that even if the true data are homoscedastic, the residuals are not. Okay, so this kind of cleans up the induced heteroscedasticity in the residuals and produces an estimator that's unbiased for the true variance when the errors are homoscedastic. So that's kind of a neat idea, but it has a limitation that it's designed for the case where the errors are homoscedastic, which is a case that you wouldn't have used this estimator anyway. But it's better than the previous ideas. So let me come to another idea, which is called HC3, which was introduced in a paper by McKinnon and White and Don Andrews, which is instead of dividing by 1 minus h, you divide by 1 minus h squared. And we'll talk a reason later why you might want to do that. But I think one interesting relationship is that you can also write the estimator this way, and you can go through the math of showing why these two are the same. But this expression says instead of dividing the squared least squares residuals by a correction, just use a different residual. What's that different residual? It's the leave one out prediction value. So what's that? Y minus x prime beta without I. X beta hat without I is the leave one out estimator. So I take the observations, I throw out a village, I estimate the coefficients, and then I use that estimator to predict the value for that village. And so that's a valid prediction. And then this is the prediction error. If I do that, I get a better residual than the least squares residual. And if I compute the variance estimator using that formula, you write it, it's the same.
It's a cluster, sorry. It's a cluster.
No, this is still at the level of individual data because I want to talk about clustering momentarily.
So what does H captures? I mean, can you explain?
So what does it capture? it captures how far the regressor is from the center. So this is the way it's written, it's a normalized length of the regressor. But if you think about data that the regressors have been centered at their mean, it's measuring the deviation of the regressor from its mean. So a large H is an observation with an unusual regressor value. It's kind of an outlier in the regressor space. It's not an outlier in the residual space. And so the kind of observation with a large H is our extreme observation. So if you have a sample of individuals who have low work experience, ranging from 0 up to 50, it might be that most people have work experiences between 10 and 20, and you have one individual who has 50 years of work experience. That is the large H individual. So it's an
X within the bracket captures the full sample.
Yes.
And then the outside one, the individual cluster sample.
Yeah, and so what happens therefore is that there's this one individual with an extreme value of H, typically the H values are very, very small, but for that one individual, they're very large. 1 minus H therefore is small. The inverse is therefore large, and that kicks up the contribution of that individual to the variance estimation, because the standard estimator ignores the fact that that individual is very influential on the least squares estimate. But if you have that person with extreme work experience, it really tilts the least squares regression around a lot, and so it contributes a lot to the regression variance of the estimator. Well, it's a good thing, because the truth is that they have a huge influence on the model. We want to capture that when we estimate the variance. If you ignore that when you estimate the variance, you're missing that. Now, you may want to delete that observation because they're overly influential. That's a different question. Yeah.
So like in previous case, in case of cluster example, so you said that there may be some clusters that have a large number of observations and that may dominate our inference. So why cannot we do the similar kind of a reweighting? So this seems to be a kind of a reweighting that you are.
Yeah.
So why can't we do the similar kind of a reweighting for the clusters that have a large?
Yeah. So we're going to get to that in a second, because I wanted to go through the no cluster example and then generalize to the clustering case, because exactly what you're saying happens.
Okay.
Yeah. In a second, I'll get there in a second. I'm going to skip over this. Another thing which I'm going to be pushing a lot is jackknife variance estimation. So this is not something which is that commonly discussed often in econometrics. Jackknifing isn't sometimes viewed in the framework of resampling, like the bootstrap, but the jackknife is a bit different. It has no randomness associated with it. So what is the jackknife estimator? It's to go through and delete one observation at a time, and then re-estimate the model, and then use that to evaluate properties of the estimator. You can use it to estimate the bias. You can use it to estimate variance. And I'm going to not be looking at bias estimation, only at variance estimation. And the variance estimator is this simple formula here. So I go through and I delete one observation, I estimate the parameter, and then I do that rolling through the sample, center at the full sample value, take the squares, and then take the sum. It turns out you don't need to take an average, you take a sum to get the variance because of the way the fluctuations work. It is known, for example, anyway, that's basically the jackknife formula. There's different perturbations of it, but this is what I'll be working with. So it's a conceptually simple method of estimating the variance. And one of the neat things about this is it generalizes immediately to anything. That is, I'm talking about regression, but you could be looking at a non-linear function of regression coefficients that you want to take a variance as, well, use the delta method. So, oh gosh, how do I take derivatives of that function? I have no idea. I have to ask the computer. So instead, just use the jackknife. That is, if my beta is a complicated function of the estimates of the model, I know how to calculate it by the leave one out principle. This could be an estimator that is a 5-step estimator. I first estimate this and I plug it in to get that. I plug it in to get this. I have no idea how to calculate the variance of that estimator, but it's easy to calculate the jackknife. It is simply a technique. And in fact, in Stata, there's something called Jackknife. You use Jackknife to any command, and Stata will jackknife it for you. Basically, you just say Jackknife to an estimator. Yes.
Properties of the Jackknife variance estimator are established.
Yes.
And then, okay.
Well, the first thing is that it's numerically identical to HC3. So the properties actually are known because we know the properties of HC3. So this is kind of an interesting fact, just that thing is different. So it's put a HC3 for the regression coefficients. Easily generalizes, that's not the case. So to repeat, when you estimate a model, linear regression, and get the regression coefficients, there's this neat HC3 formula, and then there's a jackknife formula, and they are algebraically identical. If you have a more complicated estimator, then we have the HC3 formula. But if you have a more complicated estimator, it's easy to think about doing the jackknife or computing in Stata. And then the question is, are the properties well established? And the answer is yes, because you can show that the jackknife is asymptotically equivalent to a delta method estimator. If you think about the theory, is that beta hat without I is going to be close to beta hat plus a delta method approximation. And that delta method approximation is going to be effectively the score of the estimator. And therefore, this thing is going to be close to a quadratic in the score. And the proof is based on that in this linear regression model, the deviation between the leave one out estimator and the full sample is a function of the prediction errors, and so it comes out pretty easily. Now let's go to the case that I argued is the purpose of this talk, which is variance estimation under clustering. So using the notation, you take the data at the level of a village, and then I calculate the residuals for that individual village. So that's stacking up the residuals for a village. Okay, so that's an error. How am I going to estimate the variance covariance matrix for the least squares estimator? Is going back to the work of Manuel Oriano and Liang and Zager. They independently published the estimator, which, ignoring the degree of freedom correction, remember that the variance estimator is the sandwich with the middle being sigma hat, and they simply replace sigma hat by the outer product square the residuals. So I was chatting with Manuel Oriano about this a couple years ago and saying, well, how did you come up with this idea? He said, it was just the obvious thing of taking the white estimator and then doing it for the case of clustering. White just said replace the unknown variances by the square residual. I'm just going to replace it by E hat transpose. Seemed kind of obvious. So it's kind of neat when someone says it just seemed obvious at the time, because I think for everyone else to not see it is so obvious. Now you see this big nasty thing out in front. In practice, that doesn't really matter so much, but that's a degree of freedom correction that, as far as I know, it was invented by Stata, because it's not in any theoretical paper, it's not in a single theoretical justification. It just happens to be a neat kind of correction that simplifies the n over n minus k when g equals n. So it generalizes the simple one. I'm kind of making fun of it because it's not a very smart idea, but it got embedded in the Stata. And this is the formula that's used by 90% of economists today, maybe even more. It's like I said, about 1/3 of the papers published in the AER use clustering. And from what I can tell, 95% of those use the Stata command, and the Stata command does this. So this is what they do because it's in Stata, and that's the only thing anyone ever does in from what I can tell when I look at their state of file. Yes.
The correction of degrees of freedom they're doing stata. So the thing is like why they are doing this, like for the consistency purpose, like for the asymptotic conditions you need to this.
No, it's nothing to do with asymptotics. It just people reckon. I mean, so it's just an intuition that it feels right. If you go back and look at the non-clustering case, we know that if you have homoscedasticity, you want to adjust the variance by n over n minus k so that the variance estimator is unbiased. So it feels right to do that in the case of heteroscedastic residuals. There's no real theory for it, but it feels right. So when we go to the clustering case, it feels right to do an adjustment which includes this as a special case. It is also this case that this is bigger than 1, so it makes our variance estimator a little bit more conservative. That also feels right. But otherwise, it has no real justification for it. So that I was trying to write this that this is the cluster robust variance estimate CRVE. I was trying to write CRVE subscript 2, and somehow my fonts got messed up there. But Bell and McCaffrey in a 2002 paper proposed 2 alternatives to this estimator, and I'll talk about them. And what they are generalizations of the HC2, HC3. And so there was a question about, well, what, isn't there something that is analogous in the clustered universe? And the answer is yes. So this is what they said, is that if you recall what the HC2 estimator was, it was the sum of the squared x's times the squared residuals divided by 1 minus h, where h was x squared. Well, h was x transform x inverse x. So the analogous h in the clustering universe is this funny object where this is the regressors for the ith cluster. This is the full sample. So what is this? Ugh. If I take the full sample projection matrix, it's a big n by n matrix, and then take the diagonal blocks corresponding to each cluster, I get this. So the G's are the diagonal elements of the hat matrix. It turns out that they capture the heteroscedasticity in the residuals, least squares residuals, under the assumption of homoscedasticity, just as it does in the no clustering context. So it turns out that if I calculate the variance estimator using this formula, it will be unbiased for the true variance under the assumption that the true variances of the cluster level have this homoscedastic formula. This homoscedastic formula is saying that the individual errors are IID, that everybody in the sample is independent of each other, no cluster dependence and homoscedastic. So this is a very strong, silly assumption, but it's sometimes the papers that look at this talk about this thing, a reference model or a baseline model or some sort of way of like just thinking about how to get going. It's not that it's true, but it at least gives us it's like making a degree of freedom correction that's principled rather than just being made up. And we like being unbiased. You hear the word bias, so I don't want to be biased. It does get statistician type people in trouble when we talk about bias and unbiased people. They're talking about something important, but you know what I mean. Anyway, so why might you not do it? Nobody does this. Well, one reason it's not programmed in the standard packages, but the reason partly for it is that it's relatively computationally expensive, because when you have a large number of individuals per cluster, this is going to be a very large matrix, and then you got to invert it and take the square root of it for each cluster. And so it's probably not that good of an idea in practice. Yeah.
So there are times when the estimator is not unbiased, but it's asymptotically unbiased.
Yes.
Right?
Yeah. All these things are consistent under certain assumptions. Yeah.
So when you say here unbiased, you mean which one?
Finite sample. The expectation of v hat is equal to the true value. Yeah.
when we apply this BCE or the comma cluster command, sometimes the results are those that kind of got inflated. So would it be fine, like it covers for heterogeneity across the cluster or units?
Yeah, I'm not sure. In the standard formula, so this is the formula that's always used, and but it is analogous to what we talked about before, that the when you have a cluster that's very influential, this is not, you might say these residuals are too small because it's influential. You've overfit that observation. These are too small. We really need to pump it up. And what this is doing is it's pumping it up because this is when X is big, it gets close to the identity matrix, makes this M small, and invert makes it big. And so intuitively, that's why it's a good thing.
Oh, one thing, like what ensures the invertibility of this matrix of MG, that's the partial projection matrices? Like
it's going, so an assumption. It turns out that you need to assume that this is it's not always going to be the case. Now, when is it not going to be the case? Essentially, when you have a regressor that's constant within the cluster. So assuming this will be, you need to for invertibility of this, we need to have there's no regressors that are constant within the cluster. And so that excludes fixed effects if you've left the fixed effect in G. If you have fixed effects, this G has to be the within transform data. So that, so what you're saying, what guarantees it? And the answer is, well, not necessarily. It's like, it's kind of like a full rank assumption in other econometric models.
So how does it relate if I take that MG is that partial projection matrix is invertible?
Mm-hmm.
Now, how can I relate that to the classical assumption of full rank or the full column rank of matrix X?
It's slightly stronger. Yeah, it's a slight strengthening of that assumption.
Actually, the paper says that there is a connection between them.
Yeah, but it's a slight strengthening because you at every cluster. In the cluster. Actually, it's not quite that. It's not. So this estimator uses this square root, which is computationally difficult, relatively computationally difficult. But if suppose instead of taking the square root, we just take the inverse of that matrix, we then get an analog of the HC3 estimator, and Bell-McCaffrey also proposed this as an estimate of the variance covariance matrix. We can call that CRVE3. But it's even more conservative. It pumps square residuals a little bit more. And it's numerically equivalent to the Jackknife. So here's a statement that CRVE3 estimator is numerically equivalent to the Jackknife. And what's the Jackknife? The Jackknife I mentioned before is the delete one observation. When you have cluster data, you delete one cluster at a time. So if I have 50 villages in my sample, I delete one village, estimate the model, and get my beta hat. So then I go to the second village, delete it, estimate the model, and repeat that. And then my Jackknife estimator for the variance is the sum of the squares of these deviations. And I mentioned that Jackknife computationally convenient is something like even in Stata because there's a built-in Jackknife command. If you are clustering your data, Stata recognizes that and will use this formula. It won't use the delete one observation. It will delete one cluster at the time if you have clustered variances. This equates in a recent working paper by Kinnan and Webb, where they point out this connection. Now, furthermore, see if I looks like I have a slide on this. Yeah, they say not only are they equivalent, it is amazingly smarter in the sense that this original paper by Bell McCrafrey and some others, the variance estimator this way. And no one was saying let's estimate it this way. But these said if you make the switch to the Jackknife, it can be a 50 to 100 times improved computation speed. It's just amazing improvements in computation speed. And why is that? Well, this estimator requires that you compute what is often a very large matrix and then invert it and do that for every cluster. While this estimator only requires that you recompute the estimated model for every village in the sample. And typically, when you go from a large sample down to thinking about clustering, you have a relatively small number of clusters. I joked about there being only 12 clusters, but that would be bad. But it is often the case that you might have 50 clusters, 100 clusters in your sample. And this estimator simply requires that you re-estimate the model that 50, 100, or 200 times, which is not a big deal. Relative to estimating once, you have to estimate 2 times. That's a blink of an eye in most cases. So computationally, this formula is reasonably fast. So they point out that this is a computationally convenient formula, and it's easily generalizable in the context where you're not interested in the variable, but in some of it or a more complicated object. You do quantile regression, you multi-step estimation, anything, you can add the variance because it's just simply leave out a cluster and then recompute. Yeah. So in practical applied econometrics, people all the time they cluster, or someone or them had it, or they decide to. People report cluster standard errors. Okay. One of the issues we mentioned earlier was the issue of how do we determine the level at which to cluster. And I briefly talked about that, but my bigger concern is inference. Inference means what is the property of the estimator? I want to get a confidence interval for my parameter. Perhaps I want to report a test statistic, a p-value of significance. I like confidence intervals. I think they're more informative in general, but that is what we use a standard error for. I mean, so when I said that in the beginning of the talk, in applied econometric, what we do is report a parameter estimate and report a standard error. Why do we report the standard error? Typically, it's so that at least in our back of our mind, we say that the true value, probably this reported coefficient and the standard error, and that's 95% means true value. And at least one of the things I like to emphasize is that when you think about policy work or anything else, you want to look at that confidence interval, because if the range is really, really big, you're not going to have confidence in a policy made based on this estimated parameter. And so you want to look at these things. So inference is a statement that the probability that the true value lies in this confidence interval is 95%. The inference is that 95% label attached to that confidence interval. What we know from, so that all undergraduate students are told this, that's what the inference problem is. But what we know as people who have had a bit more training is that that statement is incorrect. That is, the probability that the true value lies in this interval is not 95%. It's asymptotically 95%. It's kind of a hoped for approximation, but we know that in practice, there's an approximation error. We would like it to be as accurate as possible, in the sense that I don't want the truth to be 70% or 50% or 10%. If it's 90%, that's probably good enough. But I want, in principle, for the confidence interval to have 95% coverage, so that way I can be confident in my policy recommendations. So what are some of the problems that arise when you do cluster robust inference that get in the way of these accurate inference statements? A big issue has to do with the size of the clusters. If you have small cluster sizes, then these methods work well. In other words, if I have 5 individuals per cluster, going to work well because what I'm doing is I'm simply I'm treating families as observations, and I have lots of families, and I'm only estimating the covariance structure within each cluster. One way to think about it is that the number of error correlations you're trying to estimate. And this is what you might think of as a traditional panel. When I used to teach panel data applications in the early days, we always would say, well, you have a large number of individuals, a small number of time periods per individual. It was a be typical panel. But a lot of the modern applications of cluster regression are not the context of a small number of individuals. It's the context of a large number of individuals in each cluster. You might have hundreds of people, thousands, hundreds of thousands in some applications. You can have a huge number of observations in each cluster. And when that happens, what you're doing is you're estimating a NG times NG covariance matrix, which has a huge number of correlations. And a corollary of having a large number of observations per cluster is that you have a small number of clusters. So you're estimating a variance matrix based on G observations, and that's going to be, and that's common. And so this is going to get in the way of accurate inference. Another big problem that gets in the way of accuracy of inference in cluster regression is analogous to the problem of heteroscedasticity in regression models, and that is when you have heterogeneity in the sizes of clusters. They have some small clusters, large, because the cluster summing, which is embedded in the nature of the estimate, magnifies variance of the contribution of a cluster is large. And this is extremely common in applications. I found that I stole this from a seminar speaker at my university a couple of weeks ago. I was preparing these talks, and he gave this slide. I said, that's perfect for my needs. So the application isn't all that important per se, but what he was of observations per cluster in his application, and he had some clusters of 8 individuals and some clusters with 50 individuals. And this is the range, and this is showing the distribution. I think this was a very nice display to put in a paper. It's showing how the cluster sizes vary. And in this particular application, it was the number of individuals, number of families living on a city block. That the cluster unit was a city block. And so it's just showing you how diverse that is. And what that means is that these clusters have much larger variance impacting the least squares estimator because they have 50 observations relative to these. And so the normal approximation, we talked about asymptotic normality, is driven by this component. It's the sum across the cluster sums. When cluster sums are heterogeneous, then the variance of X prime E will be highly heterogeneous. So now I'm going to get a little bit more technical. And I want to talk about is why the problems arise in cluster robust and how to fix it, or at least partially fix it. And so what I'm going to focus on is bias. And bias in what? Not in beta hat. The beta hat's unbiased. The bias in V hat. So V hat variance estimator. We're talking about the best in the one produced by Stata, the Manuel Arellano's that. So first, let's think about you're estimating one coefficient. So I can just take the scalar, divide by the true V. So this is the variance of the regression coefficient. So I'm looking at the ratio of the two and take the expectation. That should be 1 if the estimator is unbiased. But in practice, it's not. And what do I care about? I care about if it's less than 1. If the variance estimator is inflated, it's not that big a deal. My standard errors are too big. But what I really care about for inference is too small. So if the expectation of V is small relative to V, that's a problem case. So I want to call it downwardly biased estimator if its expectation is less than the true value. And worry about the worst case because it's something I can focus on. So looking at the worst case across all distributions in some class, we'll call that B. So this is the worst case downward bias. And an estimator is a stinky estimator. That's a technical term. Fully downward biased. An estimator is fully downward biased if that is 0. What that means, can I find a distribution which the variance estimator relative to the true value is arbitrarily close to 0? It's a very bad variance estimator is small to the true value. Yeah, I'm kind of being vague here, but I'm going to be looking over the classes of all regression models. Yes.
Expected value. So
Yes.
is there an intuition for why we're looking at ratios, even if they're scalars?
No, I'm realizing this. I need to address that in my paper because it's a good question. The reason is that when we're looking across different features, the different distributions, and so I would be looking at. It turns out looking at the relevant to the question of inference. For inference, it's the ratio which ends up driving everything. And since I'm looking at an infimum across distributions, looking for the worst case is what's relevant.
One question, like what ensures that there will be an infimum? Like how can we assume that that may not exist, right?
What exists?
That infimum of the
Well, it could be 0.
It may not exist, right?
Yeah. Cases that it's 0. So if you're taking
And
because this is finite, so I'm taking an infimum over a like a set of non-negative numbers, so it's going to exist. It could be 0 though.
But that depends on your set of distributions you are
Yes.
choosing.
Yes, I'm being vague here because of don't want to. I have a more precise statement. Them, but it's like. And here's the theorem. And I'd be precise about. Here is over the class of all regression models, over all possible regressors and variance covariance structures. So, and this holds for any sample size. So you give me a sample size G, the number of clusters could be 2, it could be 20, it could be 5. Then all variance, the cluster variance estimator arbitrarily biased. The VC2 correction, which is unbiased under homoscedasticity, has the same property because it doesn't fix this problem. But if you use the Jackknife, its worst case bias is 1. Now, this is relative bias. Ideally, the expectation of V hat divided by V should be 1. This expectation could be bigger than 1. Conservative estimator, conservative being an overestimate, but the smallest ratio is 1. And this stems from the fact that the expectation of the jackknife exceeds the true value across all distributions. So it's a built-in conservative estimator.
Result here, applicable here. Why would we need
Yes, so question the reason why I'm emphasis is I focus on the worst case of trial. Now, it could be argued that these infs occur at extremely weird distributions, which you don't care about. But the reason why I think this theorem is interesting is it says that if you use what Stata reports, you cannot ensure that your standard errors aren't abysmally small. You could be with this really bad data set with very bad heteroscedasticity problems where your standard errors are just stinkingly small. If you use the jackknife, you know that's not happening. Yet, in the vast majority of applications, these standard errors will be numerically extremely close to one another. It's only in weird data sets where these things will be different. But by using the jackknife formula, you protect yourself from these weird cases, extreme cases. But so it's not really related to the efficiency of the estimator. But I'm taking the infimum to focus on this worst case. Yeah, that's next. So what it says is there's situations where the classical estimator is highly biased. And while I'm focusing on cluster regression, the same math applies to heteroscedastic regression. In that some contexts, you'll have your standard errors abysmally small. Question is a little bit about the intuition. Where does it come from? It comes from this high leverage. What's leverage? It's not to do with banking or anything. The leverage here is these regressors that are extremely far from the center of the regressor distribution. If you have influential observations, when you have extremely influential observations, that's when you get the difference between these variance estimators. That happens in an inflated way under clustering. In non-clustered regression, it doesn't happen as much. You have to have a context where you have very, very extreme regressor things, but but it can happen when you have a highly skewed distribution. Like it happens in the regression context when you have sparse dummy variables. A sparse dummy variable context is where you have a dummy variable which only equals 1 for a few operations. You equal 1 only for one operation. Now that actually, so you asked the question about invertibility of MG. That's excluded by our assumption. So it would be the context where you have a dummy variable which equals 1 for 2 observations. That's an extreme case. So, well, why would I ever estimate a regression like that? Well, a lot of people estimate saturated regressions. You have 5 dummy variables and you put all sorts of interactions. Is it really the case that all the cells have more than 2 observations? How do you really know? Have you checked? So the fact is that we don't often know when we do a regression, saturated regression, dummy. If it's the case that we don't have some sort of dummy variable which really only on the value 1 for 2 observations or 3 observations.
So one thing, like you said that regressor can have highly skewed distribution, right? So if I think about that, suppose the regressor has a kind of fat tail distribution.
Yes. So
And
that will
maybe
cause
or
this. This will cause this problem. So an example where in a simulation you can generate this kind of problem if you have log normal distributed regressors.
Or maybe the Cauchy type, Cauchy or
Could be. I haven't tried that. I found that the log normal gives me the worst results. But yeah, you can also get it with fat tail Cauchy type regressors. And this gets even worse in the clustered setting because this X prime X things tend to be highly heterogeneous. To kind of close out this morning, let me a little bit more intuition by going through an example. And this is a kind of a working example that I have in my paper, which I use to try to illustrate things. So take this model where you have an intercept and a slope, and the slope is a dummy variable. And the slope dummy variable is activated at the cluster level. So this is like cluster level treatment. So I have villages, and villages are either treated or untreated. And to take the most extreme case, there's 2 treated villages, and the rest are untreated. So I say it's the most extreme because if there really was only 1 treated cluster, then the jackknife doesn't work. Okay, so this is the most extreme I have, and then comes, and I'm going to take the extreme case where the untreated clusters have a variance of 0. So what does that mean? All it means is that the variance of the treated clusters are much higher than the others. So it's a normalization. So for simplicity, shut down the variances of all the untreated clusters, and I only have therefore variances left for the 2 treated cluster, and I'm going to be focusing on inference on the treatment slope. And in this case, everything depends only on 2 numbers. The 2 numbers are the ratio of the number of observations in the 2 treated cluster sizes. The numbers of untreated does not matter for anything. It has no effect on the finite sample distribution of the parameter of interest. So you could have millions of observations and it doesn't affect anything. And the other parameter of interest is the ratio of the 2 treated variances. This is unknown. This is known in principle to the researcher. And I'm going to first look at the variance bias that we talked about, and then I'll look at the properties of the distribution. And this is the bias of the estimator of the variance. You would like it to be 1. You'd like the variance estimator to have an expectation equal to the true value, because I've normalized it. And this is the variance of the Jackknife plot as a function of the unknown variance ratio, and I've this is plotted as a function of the rho, the ratio of the 2 treated sizes. This is 1 means that the 2 treated clusters have the same size. 0.25 means that one of the clusters is 4 times as large as the other. Okay, and these are the biases of these 2 estimators. So this is the Stata estimator. And if you have one cluster that's 4 times as large as the other, the variance estimator is extraordinarily biased. Extraordinary. This is not that unusual estimation context. You have 2 treated clusters. One is 4 times as large as the other, and they have much larger variances than everything else. Extraordinary bias. Knife estimator is almost essentially unbiased. Yeah. Okay. Oh, sorry. Barons-Fisher. The Barons-Fisher problem was the problem of diff and diff. It's the variance. It's doing inference on the difference in 2 populations. So you have one population take the mean, another population take the mean, and then take the difference of the 2. Under normal sampling with heteroscedasticity, the t ratio is not t distributed. So that was the Barons-Fisher problem. That's exactly this problem, because the difference, beta is the difference in means in these 2 populations when x is a dummy variable. So you have a dummy variable, you're interested in the slope. The slope is the difference in means. So I'm looking at the treatment effect of this, thinking of x as treatment. I apply treatment, and beta is the difference in the means in the 2 populations. And the problem is due to this heteroscedasticity, which in this case is partly due to the treatments, the unknown treatment sizes. So Barons-Fisher was referring to this. This is clustering is not typical application of Barons-Fisher. Yeah.
So I'm just asking about the so when we have this problem of sparse dummy, so you have so I'm just relating with the difference in difference. So for example, if you have a treatment group that has a lot of ones, so the treatment group is very large, and you have a control group which is very small. So you have very few zeros. So, but I have not seen these recent difference in difference estimators using Jackknife. So they are using cluster
right.
standard error. They are using bootstrap standard
No one's
errors.
doing Jackknife.
Yeah. So the problem then remains there.
Yes.
Right?
That's what I'm saying is it happens. I'm just describing here is what everybody does. By the way, we're going to break now, but I'm going to come at after the break and we start up again. I'm going to continue on this topic and not
One
jump
more
on.
thing, one more thing, like.
But I wanted to say is that this estimator is what 95% of what you see in the journals. That is indeed the case. Nobody does this.
Can you go back to that page, like?
Yeah. I think so.
So you are putting that XG is a binary at cluster level.
Yes.
So we can do this with indicator function also, right?
That's
can
a
put
dummy.
it.
Yeah. It's a dummy variable. Yeah.
Yeah. And 1G is the columns of one or.
Yes. Yeah. So this is not the only type of model that one could be interested in. I engineered this model because I knew that this would make things very extreme. So this is a design case that I know things will go really crazily bad. But I've seen many applications where this is exactly what they have, is you have a data set where you have treatment at the village level or at the cluster level. So it's not an unreasonable application. Yeah.
Yeah, you were dividing by these 1 minus HIs in the previous estimators, right? Which was not the case in the Jackknife.
Yes,
right?
that's the CRVE. This one, yeah.
Yeah. Is that at all related with these infimums behaving differently? I mean, is it
It's
like
nothing to do with the degree of freedom correction.
okay,
No, nothing
so
to do.
some sort of a regularization of the previous estimators might fix it. Is
Yeah,
that a
it's just
possibility?
it has to do with that when you have these extreme regressors, that that's all it's coming from.
So no kind of regularization might fix those.
Okay, so there's a question. Sorry. So the question is there alternative method of fixing this? I mean, that's one way of interpreting it. And the answer, I don't know. What I do know is that the Jackknife HC3 approach seems to work well, but there's no optimality the same in that this is the only method or the best method. But so people have been proposing variance estimators for the last 50 years. And this is a small class of variance estimators that have been proposed. Yeah. That's what, when I finally hit upon the fact that computationally this is a breeze, I was like, boom. So we're whatever the time is, I think I should stop. Yeah.
Yeah, tea, coffee is being served outside. Please do join us.
You can point out.
Yeah, no one can see that.
Okay.
Okay. But thank you.
Easy to find that.
I find that when I watch people doing this,
Yeah.
I just have no idea what they're pointing at. So
Okay.
that's fine. Yeah.
Second.
Okay, is that on? Is that working? It depends if I point out this way. I think it's working. It seems to be, sometimes it. There, yeah. Sounds good. Yeah.
Well, good morning again, and welcome back to this second session of this morning. Well, all of us are very well aware of the importance of clustering, as Professor Hansen has mentioned. He mentioned in the morning that almost over 30% papers are using clustering, and even I was not aware how the standard errors has been calculated by the Stata, but blindly using all those commands until now. So it was eye-opening and learning thing that sometimes we should also open up and see what's happening in the program as well, if we really want to know that what exactly errors are that we are calculating and what we mean to calculate. So whether there is a correlation between them or not. So anyway, so in the second session, Professor Hansen is going to discuss about two-way clustering, and I'm sure that we'll learn something more exciting things as we did in the morning. Thank you.
Thank you. I'm going to continue first with, because the two things are all interrelated. I'll finish up talking about the cluster regression model, and then also talk about two-way clustering. We had a lot of discussion going on, and we didn't have time to have lots of questions at the end, but we had lots of questions during, so hopefully, but feel free to interrupt with more questions. By the way, I was reminded just a minute ago of the story that is, as people might realize, sometimes you don't have a choice about like what the cluster size is or anything else, because maybe the study is given to you and you might not, so things might be awkward. I'll give, because the example I had was I was presented with an empirical study that someone had written that was being used for the basis of a policy decision being made by the U.S. government, and the part of the policy change was based on this study. This was serious, and I spent some time trying to convince the chief economist at this government agency that this was really nutty, because it was a study where there was effectively 12 clusters. The cluster was a bank, and there was one treated cluster, one treated bank. And so they're making a policy change based on the fact that they had a sample with 12 banks, only one of which was treated, and they're making a big inference on this. And I thought it was nutty, but Congress passed it because politicians make decisions probably based on politics rather than on science, right? But it's still the case. Sometimes that's all the information you have. You can't say, oh, go gather data on 100 banks and do 50-50 split on treatment, because that's simply the data you have. So to review a bit, I was trying to go through this little toy example, because I think that this toy example is just trying to give insight into how things can really go bad and how you can protect yourself. Okay, so once again, the problem is that we have cluster level data with a simple binary treatment at the cluster level. So a cluster is either treated or not treated, and you're interested in the difference in means. This is the Barron-Fisher, the difference in means between treatment and non-treatment, which is the same thing as the slope on the dummy variable. Okay, but this is the extreme case is when you have a small number of treatments, and I'll focus on There's 2 treated clusters. And what you find, as I said, is that the standard errors that are reported by the packages can be arbitrarily biased. One is the case of no bias, and small numbers are that the standard error is biased towards 0. And you can have arbitrarily bad bias by the standard method, but not if you use like the Jackknife, which is conservative by construction. And that's this theorem. So Jackknife standard errors are never too small. They're conservative in the sense that they're not downward biased. But you're not really interested in standard errors per se. What you're interested in, as I mentioned earlier, is confidence intervals or perhaps test statistics. Oftentimes in theory, we talk about hypothesis tests, but there's a known duality between hypothesis tests and confidence intervals. So I'm going to focus in the theory about the properties of hypothesis tests. But in practice, you really want to think about this as, well, this produces nice confidence intervals. So for inference, what you do is use either asymptotic theory or finite sample theory. But I'll be using finite sample theory because it gives insight in this particular context. So assume the error is normally distributed. We don't really believe that truth about the world, but it gives us insight into the distribution's finite samples. You then have a t ratio, parameter estimate minus true value divided by standard error. And we're going to be thinking about 3 different test statistics. The one that Stata produces, the cluster robust, this cluster robust 2, 1, and one based on Jackknife. And a test rejects if the t statistic is bigger than a number like 2, 1.96, right? And could either use a normal distribution or a student t approximation. The difference is typically negligible.
One question.
Yeah.
We're assuming that for the finite sample, it will be a normal distributed.
Yeah.
Now, if this assumption underlying the fact that errors are IID?
No, it's that the error distribution is normal within cluster correlation. So the errors are normal, but not and independent across clusters, but within clusters, they have arbitrary correlation.
And also like for the part like in the finite sample theory, if it was not normal, like non-normal distribution, then we could have got by the central limit theorem that
Yeah.
will go to normal.
Yes. So everything is, yes. But the normality is going to give us a insight into the finite sample distribution, which is going to be sharper.
Thank you.
And here is the result. So this is so one thing is that an asymptotics typically is if you have large samples, everything works wonderfully. Don't worry, and just don't worry, be happy. But in the finite samples, things tend to be worse. That's why looking at the finite samples is more interesting. And what we're interested in is the probability for distribution theory, the probability that a test statistic exceeds a critical value. So if the critical value is 2, we would expect that number to be 5%. The probability that the t statistic exceeds this. And if that number exceeds 5%, we call that size distortion, that the test is oversized. That's a bad thing. Now in practice, if the test instead of being 5% size is 8% size, 10% size, we say, that's okay. You know, we're willing to live with that. But if the size is 20%, 30%, it's bad. It means that you're rejecting frequently. But when you use the cluster robust standard error, which includes the heteroscedastic standard error that we also use, the size can actually be 100%. You could reject all the time. Why? Well, we learned previously that the standard errors can be arbitrarily small. That's essentially the why. If the standard errors can be arbitrarily too small, it can be the case that your test statistic rejects too much. Notice I have their arbitrary C. This holds for any C. You tell me that the critical value is not 2, but 10. You can be really conservative. You can use critical value 10. Same thing holds, that I can find you a distribution so nasty that your t statistics are bigger than 10 with probability 1. So that's saying that things really stink, the conventional standard errors. Same things holds when you use the what's called the CV2, the cluster bus correction doesn't improve things. But if you use the Jackknife, which in the regression context is HC3, simple state of command, or the Jackknife in the cluster robust case, then this probability is bounded by the Cauchy distribution. So this isn't perfect. I would like it to be the normal distribution. Yes. Yeah, the wild bootstrap, I don't have a theorem to describe. So the question is, what happens if you use the wild bootstrap? I don't have a theoretical investigation of that, but in my simulations, I find that the wild bootstrap does not solve the problem. Yeah, yeah, the fact is I haven't done this for a while, so I don't know. Yeah, I don't have a full answer. I mean, I remember that it does better than the asymptotics, but doesn't solve the problem. The problem is that this extreme leverage, the bootstrap just is unable to really fix that. So this distortion is not, say it's a finite sample result, it's not solved by increasing the sample size. This holds for any sample size. You give me a sample size, 100 observations, 1,000 observations, 1,000,000 observations, and it's still the case that you can find a sampling distribution where the test arbitrarily over rejects. It's entirely due to extreme regressor leverage. It's not, and part of the thing here, this is holding even though the error distribution is normal. You probably learned at some point in a class that when the error distributions are not normal, then bad things can happen. But this is with normal errors. You may have learned that bad things can happen when you have serial dependence. There's no serial dependence per se here. Everything, it's cluster dependence, but that's not the source of the problem. It's extreme regressor leverage. So that really stinks. What we find instead is that the Jackknife t-test has a bounded distribution, and it's bounded by the Cauchy. You can kind of think of that as a t distribution with a really bad degree of freedom. The Cauchy is the student t with 1 degree of freedom, and so you still get size distortion, bounds the size distortion, and a conservative person might say, then I'm going to use the Cauchy distribution instead of the normal or student t. I don't recommend that because that's excessively conservative, but it at least says in principle you could do that. Instead, what I'd like to show you is numerical calculations of this. So if we look at we're looking again at the rejection probability of t-tests. And in the model that I described to you, the very, very simple Behrens-Fisher problem, again, we just have treated clusters and untreated clusters and arbitrary and these heteroscedasticity properties. There was only 2 parameters that matter. Rho is the ratio of the number of observations in one treated cluster versus the other. And then there was a phi, which is a variance ratio, the variance of the ratio of the variances in the 2 treated clusters. So I'm going to fix rho at 0.2, which means one cluster has 5 times the observations of the second treated cluster. It's not unreasonable. It's kind of trying to make it a little bit extreme, but not too extreme. And then I'm going to vary the variance ratio. The variance ratio is the variance in the 2 clusters. And I'm going to plot here the type 1 error of the test. So the type 1 error is the rejection probability that the test exceeds 1.96. If the tests are perfect, they would be rejecting 5% of the time, which is the dotted line. So numbers above that are saying the test is over-rejecting. If they were over-rejecting a little bit, we wouldn't be too excited. But above 25%, and you're just doing something really, really, really bad. The dashed line up here is what we all do. What we all do is use the standard cluster robust standard errors, which includes the heteroscedastic standard errors in classical regression. And it says that in this extreme context, this variance ratio can be any number between 0 and 1. These are the range that it can take. The best case is that the two variances are about the same. In that case, the test rejects about 40% of the time. That's horrible, 40% rejection rate. But if this variance ratio is extreme, the rejection rates can approach 1, which means that the T ratio is just excessively sized. If you do this correction here, it's not that much better. One thing I didn't mention, by the way, is that this correction here, the CRVE2, was recommended strongly in a recent paper by a guy named Guido Imbens, you may have heard of. He won the Nobel Prize a year ago. So Guido and his student Michael Kolazar have a paper in the JBES a couple of years ago talking about finite sample corrections and cluster robust inference, and they made a big case that this is what we want to do. They do more in the paper than that, but this is one of the things they do. And part of the point here is that it helps, but it doesn't help that much. You can do much better by using the Jackknife, which is the solid line. It's not perfect, but it pulls the over rejection rate down. And the most important thing, which I want to emphasize, is you don't get the unbounded feature, is that the worst case is not infinity, well, 1. So I submitted this paper, by the way. Someone was asking, is this paper available? And the answer is yes, it's on my webpage. And it's under revision because I submitted it, and Guido was actually the editor. He rejected it. But one of the questions the referees raised is that, well, this distortion is still pretty bad. Shouldn't you do something better? And so that's part of the thing. I'm trying to, fix up this problem, that it's not 5%. You want this squashed down. But the basic, what the message is from this, and then I'll skip over this. Yeah, this is not. So to summarize this discussion, my bottom line is it's very useful to know what the formulas are in the back, so that we know what we're doing when we press the cluster command in Stata. But I think we can do better. I think we can do better, and by move to the Jackknife, move away from the cluster robust formula, move to this Jackknife formula. I think it's more robust. In the vast majority of applications, you won't see any difference in the estimates. And the estimates are variance estimates, not the coefficients are the same. The question's the variance, the standard error. Most cases, it won't make any difference. The only case it makes a difference is when it's really important. So then, what should I do? And the answer is always use the Jackknife one, because protected from the worst case, you don't have to think about it.
Jackknife, should we still be using Jackknife?
I'm going to go talk about that now. And the answer is, I don't know the answer to that question. I wish I did. But and so this is kind of my recommendation, and it's not by the way, there's no perfect recommendation. That you notice that there's still distortion problems in the statistics, so life isn't perfect. And I wanted to mention. I guess I didn't have. I'd say what the other practical. I'm sorry, I have it here. Important issue always is, well, how am I going to do this? Do I have to spend 5 years programming to do my answer? And the answer is no. If you work in Stata, which is just fine. I mean, you also do these things in R. For non-clustered regression, the way to get the efficient way to get the standard errors is not with the Jackknife, but is with this command, VCE, variance covariance HC3. Gives you the efficient calculation of the standard errors. If you're doing clustered regression, this would be the command, VCE Jackknife. You have to tell it, of course, what you're clustering on. And there's different ways of implementing the Jackknife. The way I've described it to you is similar to what they call the MSE version.
One question, like in the last slide, you showed that bounded size distortion.
Yeah.
Right. What is that exactly? And I saw the Jackknife is bounded by the Cauchy distribution.
Yes.
Right. But in the case of Cauchy distribution, sometimes the moments do not exist.
Yeah, we don't. So this is you don't even worry about moments because this is the distribution of the T ratio.
Okay.
And so you have critical values, quantiles of the Cauchy distribution. So for example, if you wanted to be really conservative and use the Cauchy distribution for inference, it means that you replace 1.96 by 12. So if you use 12 as the critical value, then you have guaranteed inference. It's very, very conservative. But so it's no problem in moments. It's just that the critical value is increased.
And what do you mean by the size distortion? Like in the simple
Is that size is not 5%. Size is some other number. So as I showed you, the size could be arbitrarily close to 1. Size is the worst case rejection probability of the test statistic under the null hypothesis. Size distortion is when the size exceeds what you thought it was. I say what we thought it was, we call that the nominal level. The nominal level of the test is 5% typically. It could be 1%, but whatever it is, that's the nominal size. That's what the size you tell people, but then you get something else. The same thing's true with p-value. Suppose that you compute a t ratio and the t ratio is 2.5. And then you calculate the p-value and the p-value is 1%. So you report that. That's a smart thing to do. Size distortion is the statement that the true p-value is not 1%, it is 10%, 20%, some other number.
Okay, if I understood you correctly, when we had the non-clustered regressions, if you use the Jackknife, then you could actually also use them for nonlinear estimators.
Yes.
So it had nothing to do with the least squares. It had nothing to do with linearity.
Yes.
Does that logic carry over to the clustered regression? So I have a clustered regression, but I have a nonlinear estimator.
Yes.
And I can still do asymptotics. If I have a large enough sample, I can still go and do precisely what you've done.
Yes.
What you've done does not depend on least squares, nor does it,
These exact calculations and describing these problems are very specific to least squares, but
the results.
Yeah, but the general idea.
Set of results.
Yeah,
for...
I mean, one question I've wrestled with is that if what I'm saying as a general methodology is let's use the Jackknife in more general, it'd be nice to have a theoretical justification for that. It'd be nice to say, here is a reason why in this nonlinear context it's a smarter thing to do, and I do not have that justification. I say it works better in this regression context, and therefore by intuition and analogy, I expect it works better more broadly.
Theoretical results for the non-clustered case.
Yes.
Because of the equivalence.
Yeah. Well, we know that the Jackknife is asymptotically equivalent to, but that doesn't mean that it's better. It'd be nice to say that it is better, but we do know that it's asymptotically equivalent to what you conventionally do.
So I have slightly different question. Since we are discussing the dynamic panel at the beginning, suppose the intra-clusters observations, the correlations change over time. So what would happen?
I have no idea.
I mean, because since we are rationalizing some kind of correlative will be there between the samples within the sample, but that dynamics can also be changed.
So one of the interesting things I think going on in a lot of modern econometric work is people are looking at all sorts of treatment heterogeneity, and if you generalize that to thinking about coefficient heterogeneity, and that includes coefficients that change over time, what happens when we use our conventional procedures in those contexts? And the general answer is lots of things can happen, and in general they're not good. So I really don't know the answer, other than it's very, I mean, it's a very interesting question.
maybe, we could actually use at least generalized.
Yeah.
Divide.
But yeah, in fact, I suppose that one of my deficiencies in my own work is I spent too little time investigating questions like that, and I see a lot of the young people really focused on this kind of heterogeneity, and it's exciting because that's the real world. The real world, we don't really think that everything's all constant and homogeneous. Everything's different. I don't know.
Same thing also go with the spatial correlation. Let's say inter-clusters correlation as well.
Yeah. So anyway, I was just trying to say that these two commands are fairly simple to implement. This doesn't quite do things exactly the way I described. It has a couple. So I want to make things a little bit easier. So I have a research assistant working with me, and we have developed a stata command. I think I'll call it JRegress, but it's not yet available. That implements this much faster than the stata command. The stata command does all these robustness checks, but we have a very efficient. It's amazing how fast it is. Command to calculate the regression coefficients and standard errors, and also a similar command for one that this kind of stuff isn't as easily available right now in R. So we're also my research assistant is also writing code to do the same thing for R, and so hopefully it'll be more available to everyone. No, hopefully it's not. I mean, so the idea would be is that you would use this command JRegress instead of regress. It'd be kind of that simple. So I'm going to switch. Sorry, questions. We've been having lots of questions. Questions or thoughts? Because otherwise, what I will do is I'll jump to discussion of this two-way clustering, which relates to the question that raised a moment ago. But feel free to go back. These things are all interrelated. So I need to change the slides. Maybe I don't want to play with this too much. I want to change to a different file. Yeah, lecture 2. Yes, please. Hopefully this. So again, I just need. Okay, there we go. Thanks. Okay, so the slides aren't formatted quite the same way, but it's referring to a joint project, as you can see, with 2 co-authors. And but I want to use it as a mechanism to talk about another type of clustering, which I think is going to become even more important in econometrics over time. I think we're going to be. I've said that in the last 20 years, we've seen this evolution that now really a huge swath of our applied work has clustering. But a more complete statement of that is that you see that a lot of papers have complicated clustering contexts. It's not just the simple clustering I described before of people who divided into groups, but oftentimes there's even more complicated interdependent clustering. One type of clustering is two-way clustering. You can also have three-way, four-way, and you can have spatial dependence. There's lots of different kinds of correlation patterns that are possible with economic data. And so I don't want to say that this is the only thing, but one type of clustering that seems particularly relevant is two-way time series, two-way clustering. And this particularly turned out to be relevant in a lot of kind of applied finance, where people work with firm level data. So you follow firms over time. So you have a sample of, say, 500 firms or something, and then you watch them over 40 years or quarters. And but you could have other contexts where this arises as well. But the general context is that you have individuals and time. So what we're going to be focusing on is, in this context of two-way clustering, is standard error calculation and providing theory that it works well. And so to get at the notation here is, instead of thinking about individuals and clusters, it's going to be individuals and time. are going to be the two indices. And because a major part of the applications are these finance firm level, we're going to be using the metaphor of firms in time. So individuals are firms. And so I is a firm, T is time, and that you want to think that the data, so that's the context, is that you observe firms over time. And then we're going to be looking at regression models, regressing Y on X. Okay, but so all the data is going to be indexed by I and T, firm and time. But now we're going to need a model to try to describe where the data comes from. And that turns out that the workhorse data generating model that works well for that is this type of model. Explain what it means and why it's relevant and what its implications are. And it says that the D for data is generated for individual I at time period T by three components: a firm component, a time component, and an idiosyncratic component. So think about this like in panel data where you have individual effects, time effects, and idiosyncratic, but we're going to allow it to be nonlinear. This is, you could have it be linear, and we're going to work out a linear representation, but to have it more general, you can think of it as, but what are these? This is that, so we're looking at, say, investment behavior by a firm, and but there might be some firms that always invest a lot because of the nature of their firms are. But then there's also things that are affected by time in a way that systematically across all the firms. So, I mean, yeah, that if you take one individual firm, they invest a lot in one year and not so much in another year. But what we're also interested in, that they all move together. So there's years where lots of things happen. There's years where not a lot of things happen. You can think of this as a business cycle. So you have a business cycle effect, a firm effect, and then there's the epsilon, the idiosyncratic. Now, we'll be treating for a lot of the work that epsilon is have it some sort of serial correlated stationary process also, without too much change in much of the work, but it's the basic model. Well, intuitively, I think this makes a lot of sense. It's not a complete description of the world. It could be that you want something that's more complicated than this, but it seems to capture the fact that we have things that are common for a specific firm, things that are common across firms at a given time, not. And what happens when you have data that's generated this way is that means that the data is now correlated across time for any individual and across firms for any period of time. Because see, this is correlated, this is common for all time periods, and this is common for all firms. So the model we talked about before about one-way clustering, it's kind of model that you have a component that was a firm component that was common, but now, and if you omitted this would be opposite type of. So you could also have one-way clustering where it's just based on a time effect. You could have one-way clustering in where the correlation is across time for given integers, or it could be across firms for a given time. If you have both effects, it's like double clustering. And once you have that, you don't have any more of a simple way of splitting up the data. So with clustering, I can say, well, look, I have these 100 villages. I just take the 100 villages and puts them in different parts of the spreadsheet, and they're all independent of each other. But that's no longer true here. I can't like take this observation and that observation and say that they're and divide them up into independent groups because everything's connected up in this way. And so it destroys the whole process that we had before. So the prototypical basic model we're going to assume is that the epsilon, we're going to assume that these things are mutually independent and that the epsilons are all IID. But so that this is part of the limitation of this framework is this assumption independent across groups is going to be really important. Yeah.
So if we take the financial market, suppose now in the financial market, that epsilon IT is the idiosyncratic risk, you can say. So you were saying that they are IID, okay, but in finance, like
Yeah. Oh well, but yeah. So for our basic model, but generalizing this to some sort of serially correlated heteroscedastic process isn't going to be really important. What's really important is that it's independent from this component. That's what's really important. Is that these groups are mutually independent. But those are limitations of the theory. Yeah, it's not perfect. So you start off by thinking that these things are independent of one another. This is like and this is, you have firm 1, which is Twitter, and firm 2, which is Apple, and all that. Now, Twitter might be a bad example because the Twitter before and after this guy Musk are not the same firm, but in general, you think that there's something like constant about a firm over time. And that is reasonable to think about as being mutually independent. That is, the firm 1 is independent of firm 2, is independent of firm 3. That's a standard way we go about thinking about these kind of models. Now you might say, well, that's not really true. Aren't firms interrelated? So, oh yeah, but you have to, this idea that firms are independent of one another is kind of a basic building block. It's not surprising. And as I mentioned, we're going to be assuming that the epsilons are IID. That might be stronger than necessary, but it's not that big a deal. But now let's think about gamma. The gamma is this thing like a business cycle effect, the thing that is commonality across firms. That would be nutty in many applications to treat as independent over time. That is, if I'm thinking about a business cycle, it's quite reasonable to think that neighboring years are correlated and further years are less correlated. So it would seem natural to think of this as, while it's independent of we might have independence across the firm effect and the time effect. We don't want to think of the gamma as an IID sequence. We want to think of it as in the time language of time series, a strictly stationary mixing process, something like that. Maybe you want to think about it as a random walk in other models, but that wouldn't work for our needs. But we're thinking of it as, in the language of time series, a mixing process, but something with serial dependence, but not independent. So that's them here. So it turns out that's an interesting complication. So now we want to talk about estimating standard errors. You could do one-way clustering. That's what we talked about before. But then we have this two-way dependence. So we want to do two-way clustering. And there's a famous paper by Cameron, Gelbach, and Miller with a small number of citations of 3,000. So this is like to be a 10-year-old paper with that many citations means that this is something that people actually use. An interesting bullet point is that they propose this method but don't have theory. That's just something which and there's also a recent paper by Menzel and some other papers. Anyway, and there's this other paper by Thompson, also 2011, which is related also and doesn't also have theory. So what we're trying to do is add some theory to try to understand these things. So this is some related literature. So what again is the basics here is that analogously to the cluster regression context, we're thinking about a linear regression model with a conditional mean 0 of the error, and you do least squares. But now instead of summing over clusters, we're summing over individuals 1 to n and time periods 1 to t, and we're going to be assuming for the purposes in this paper of homogeneous cluster sizes. So I'm violating my whole big thing about that cluster sizes are heterogeneous, because in this literature of the financial applications, typically they do have homogeneous cluster sizes. You observe all the firms for the same years. And so it makes things a lot easier, and so that's what we did here. Now, you estimate this by least squares, and then what we're interested in is the variance of beta hat. And what happens when you do the variance of beta hat? Well, I don't know how if you teach econometrics or statistics, but when I teach econometrics and statistics, what I do is I take, well, look, the variance of the sample average is that you take the sample average, you multiply it by itself, and then you notice you have all these cross terms, and then you say, okay, now let's calculate the cross expectation of all these terms and see what appears, and you find that the variance of the sum is just the sum of the variances because all the cross terms are 0, except if you're teaching time series. If you're teaching time series, you find that all the cross terms are non-negligible, and that makes it complicated. Well, let's think how it happens in this context. I have I want to talk about the variance of the central component of the matrix. And what does the matrix have to do with is I have these things which are these subscript I components and the subscript T. That is, I take my regression score is X times U. Then I take the time sums. I take the sum over time, where I take the sum across individuals. And I have these like cross-section component and this time series component of the regression scores. And then I compute the variance of the whole thing, and I find that I have something which is based on the variance of these cross-section components. I have a component which is the variance of the time series components. So I have like the variance of this and I have the variance of that. But guess what? You do a double counting when you add the two, because the simple variance of X times U is counted here and here again. So I got to subtract that back. So I have the variance across individuals, and I have the variance across of the time parts, and then I subtract off the common component. But that's not it. I also have a part that represents zero correlation. So I also have a sum from across lags of what? This is the correlation of S is the time series. It's a sum across individuals. So this is like the time component. This is like the time series component of the regression score at lag M. So I have this time series component of the regression score lagged by a number of time periods, and its cross correlation. So if you do time series, you're familiar with these heteroscedasticity and autocorrelation consistent standard error calculations, and it has to do with the time series correlation of the regression scores at lags M. And so this is lag M, and then you have potentially the correlations ranging from 1 lag up until T minus 1 lags. So I have a T by T covariance matrix over time, and I could have correlations from lag 1 up to through lag T. So it gets really complicated. But when you calculate this, you also do this double counting again, and so you have to subtract off the correction for the own variances. I don't want to kind of get into this too much, but the basic point is that the variance of the regression estimator depends fundamentally on a variance which is like a one-way clustering of the variance of the cross-sectional correlation, a one-way clustering in the time series dimension, and then a component representing the cross-time correlations, the correlations of the time series component at different time periods. These three are the fundamental components, and these are two minor corrections to deal with over counting.
So why are you doing that GM plus GM
transpose? So this has to do with that I want to look at the correlation of it's a symmetry in the covariance matrix. It's counting the correlations both forwards and backwards. It's just I didn't go through all the accounting, but it comes when you account. This is these things are it makes this matrix. This is not a symmetric matrix, but this makes it symmetric.
And another thing is, why, like, what is HM? You explained, right? I couldn't get it. Like, what HM is doing here? It balancing the GM part, right?
Yeah.
Cost parts.
Yeah, and then this is getting rid of the double counting.
And also in the HM part also you are doing that symmetry.
Yeah.
HM prime.
Yeah. And so this is really an accounting exercise of looking at all the correlations that are possible. I mean, they could be are zeros, but they're all potentially there. There was another question. And so this is again kind of a statement of it that the this one here I'm now kind of explaining here that I have variance of the firm sums, variance of the time series, and the autocovariance of the time sums are the three components which relate to the variance of the regression estimator and are things that you potentially want to account for in the regression analysis, in the standard error calculation. And so this is the variance of the central component of the least squares estimator. To get a standard error, we want to estimate the variance. I don't know what it is. I have to use sample components. And so typically, we just replace the unknown expectations by sample averages. This is equal to the natural estimator of the first component is the one-way clustering standard error estimator. And similarly for this, that is, we're going to estimate omega by omega by omega hat, where this component is the average of the variances of the R's. I'm going to use the averages of the empirical R's. What is empirical R? So it's the sum across time of X times the residual. I take the X's and multiply them by the residuals to get my regression scores, and I take the averages across time and I get my cross-sectional things. And that's just really the cluster. This is the one-way clustering estimator. Similarly, is this component, this variance of the time sums, I just replace this expectation by the sample version. And then there's this correction, which you can kind of ignore. Then finally, this part here is the autocore variances of the time sums. I have lots of autocore variances, but each of these I estimate just by the empirical version of this. I just replace that G by G hat, the empirical version. But while I have T time periods, I have potentially T autocovariances that I want to estimate. We know from the literature and heteroscedasticity, autocorrelation, consistent covariance matrix estimation that that's impossible. You can't estimate all autocovariances. You can only estimate the small ones well. So I replace the sum over all autocorrelations by the sum of M, where M is a small number. Furthermore, I want to use the small correlations a lot and the high correlation, the long lags only a little bit. So I multiply by a weight function. The weights we're going to use are called the Newey-West weights. We're going to use the Newey-West weights, which down weight as you look at longer legs. So fundamentally, this is an adjustment to the first components, which is like a Newey-West covariance matrix estimator for cluster sums. This is a weight function. The number M is sometimes called the lag truncation number in the time series literature. It's a tuning parameter, and we're going to have to pick it. No, the assumptions really don't play too. This calculation here, by the way, had nothing to do with that modeling assumptions. Yeah. Yeah. So the basic, I think the big part of where the assumptions come to play is that our assumptions give rise to the idea that these correlations are going to decline as the length as M increases. As you look at long autocovariances, these cluster sums are going to become more independent. That's stemming from the assumption that the gammas that we're assuming to be mixing processes. If they were random walks, that wouldn't hold. So it's hard for me to know to what extent our assumptions drive everything else, but that's kind of a key one here.
So
There's all,
two things, like first thing is the weight function you mentioned. Are you estimating that function? Just taking it from the new West? Okay.
yeah.
And-
So in principle, it's like coming from the kernel literature. It's parametric kernel estimation.
Okay. And the second question is, you are taking the estimate of capital sigma, the omega, I think,
Mhm.
omega, and taking the inverse, right?
Yes.
So what makes sure that the inverse exists?
Luck.
Nothing.
Yep. Yeah, it's something we have not solved. So one way we could solve it is that this estimator here is, this is positive, this is positive, this is positive. If you ignore those two. So if you don't make these corrections, you would end up with something that's positive, definite, for certain. But with the corrections, it's not guaranteed. And in our Monte Carlo work, not one single sample where it was not invertible. So we don't know, but it's really not guaranteed here.
Yeah, I think I don't understand this particular point over there. So you started with, you choose one particular lag, and then you take auto covariance
Yeah.
of all of that, and then you sum over all the lags.
Yes.
Like, what is this capital M doing? Is it like truncating till
Yes.
what lags you are?
Yeah. So
And why is this required?
because if you estimated, you wouldn't have a consistent estimator of covariance matrix. Now, in the time series literature, one approach that's been proposed is to that allow this number here to be large, and then you can have a covariance matrix which is asymptotically random and account for them. We did not do that. So, but in principle, but you can't have it literally equal. You have to have some sort of weighting, otherwise you get a very bad estimator. Yeah, if you follow the Vogelsang approach of thinking about large lag truncations, M is large, then the standard errors tend to be larger. They're random. They're larger. The inference is non-standard, and you have to correct for that. And we simply didn't go that route yet. One of my co-authors said, "Should we do that?" And we did not. But that would be like another paper. So just to try to contrast with the literature, the previous talk was talking mostly about one-way clustering, which is this estimator. Using different notation, but it's just the first line. So our estimator is all these components. One-way clustering is that. But you could also do an alternative one-way clustering where you cluster within time, and that's just this component, ignoring all these. And then there's this famous paper by Cameron, Gelbach, and Miller, which ignores the weights. So it's one-way clustering corrected for double counting, assuming there's no serial correlation in the time series component. So their estimator does not have this. That's literally, this is the algebra. If you go and look at this Cameron, Gelbach, Miller, this is their estimator, or use their data code. This is what it computes. The question was like, what is actually an estimator doing? This is what Cameron, Gelbach, and Miller do. An advantage of their estimator, by the way, is there's no tuning parameter. You just do one-way clustering in both dimensions and then correct for it. And so it's very simple. Yeah. We'll get to that. Yeah, no, but well, I'll talk about that later. Yeah.
So just staring at this, if we were to allow serial correlation across the clusters, would it be too simplistic to say that there would be an additional term like that?
Oh yeah. Oh gosh. Yeah. So yes, that would. But okay. The nice thing about serial correlation in time is that it's a nice ordered thing. There's just one dimension. When you have serial correlation across cluster units, then you have to have a model for that. And so, like firms, like how would you model that the firms are correlated? you'd have to have a model for that. Yeah. Then you could say that the neighboring states and stuff, that you can do that, but it's complicated. I mean, there's a lot of work now looking at spatial correlation and everything else, and we did not do that. But yes, it's going to add terms and make things harder. Well, just it wouldn't be a simple one-way sum. It would be more complicated because the dependence is not just one-dimensional. Yeah, there was a question. Well, we did not develop S, but if you go back and that's an interesting question. If you think about the original Hal White paper on covariance matrix estimation, the paper about testing, not a variance estimation, saying that you compute the variance. That would be the test. Yeah, I presume so. I mentioned there's also a paper by Sam Thompson, and what his estimator does is it doesn't use these weights, just uses simple uniform weights instead of the weights as one. And in fact, his paper also goes further and says M equals 2. Just use 2 legs. That's not really it's not a theoretical statement. It was just he said, in practice, that's all you need to do is look at 2 legs. So that's yes, how do you pick the tuning parameter? Thompson says 2. So another way of thinking about this, trying to get some more intuition about what we're talking about, is that you can think of time being organized this way, and cross-section units are being organized this way, that any individual observation is a cell in time and units. And under the assumption of IID, they take time period 1, individual 1, that observation is independent of everything else. If you say that we have dependence within firms, which is kind of the standard one-way clustering model, says that firm 1 is clustered over time, is dependent across time, but is independent of everything else. If you think about dependence within time, it's the statement that at time period that observation is correlated with other firms' behavior in the same time period, but they're independent across time. So it's that opposite kind of flip. The Cameron, Gelbach, and Miller two-way dependence that is extremely popular in this applied finance literature says that this observation is correlated, so firm 1, time period 1, is correlated with other time periods of the same firm, and is correlated with other firms at the same time, but is independent of other time period firm combinations. So that firm 1, time period 1 is independent of firm 2, time period 2. That's the basic two-way assumption that they're making. The Thompson assumption is that this observation can be correlated up to 2 time periods away with different firms. So firm 1 is potentially correlated with firm 2, 1 period different. So that there's a spillover effect in the correlation, but it's independent more than 2 time periods away. The model we're talking about says that this observation is potentially correlated with everything in the sample, but the correlation diminishes as you move across time lags. But you have arbitrary dependence across time for any given firm and across firms at every given time. And so these correlations are left to be unstructured. But if you allowed for arbitrariness, that'd be too much. So we force it that you have diminishing correlation as you move across time periods. This is one pictorial way of thinking about the kind of dependence we're talking about. But in all of these, once you get beyond, sorry, let me, now remember how you want to think about variance estimation is that the neat thing under this IID assumption is pretty easy, is that the variance, all you do is you take the variance of each individual observation and sum up. In this context, what you do is you take these cluster sums, and then you have independence across individuals. In this context, you take these time sums, then you have independence across time. But in this Cameron-Gilbach-Miller even two-way cluster, you can't do that. There's no way of breaking the data up into independent clusters, because every observation is correlated with everything else. So the only way to do that is to do the clustering this way and clustering that way. And then when we get to these contexts, we have to add in this extra smoothing. Now, is this important? This is taking an example. These are two different examples, two different applications of where we took a time series and then estimated the components. So we started off with saying that an individual model for a panel data is that it depends on an individual firm effect, an individual time effect, and an idiosyncratic component. It's not too difficult in that framework to estimate these fixed effects components, right? And then once you have them, you can plot them and see what they look like. And so this is a plot of the time effects for a stock. This is not the stock level, but it's the returns. And this is a Tobin Q example. And so the point here is the estimate of the time effect. And then the bands are showing you an estimate of the uncertainty of that effect. And so this is an estimate of it in my earlier notation of the gamma, the time effect that's modeling in here. And the Cameron-Gilbach-Miller model says effectively that gamma is serially independent, that it's an uncorrelated time series. So I can just do the simple two-way clustering. But notice these numbers are all positive. Notice these numbers are negative. This looks like a swinging pattern. Here, these are all negative, and those are all positive. If you do time series, you would look at this and say, yeah, that's a serially correlated time series. And this is Tobin's Q. Why would you ever think it's an IID process? I mean, it'd be kind of nutty. So here, this is an estimate of the common time component, and both economic reasoning and the data tell us, yeah, it's a serially correlated process. It's not surprising. It's not. I mean, any applied person I've talked to and describing the model and saying, and we want to think of gamma, the time component, as being serial correlated. Everyone I've talked to said, yes, of course. Of course we want it to be serially correlated. And these are estimates of the autocorrelation. If you don't like pictures, if you like numbers, this is the autocorrelations, the same thing. And so let me kind of get through a few of this. So anyway, just there's more discussion of the estimates. Okay, question came up, how do we pick the bandwidth? Bandwidth is M, and here's the answer. Woo, where did that come from? We just made it up. No, the answer it came from is that there's an old paper by Donald Andrews who worked out the optimal bandwidth in the terms of minimizing the mean square error of the Nui West estimator. And then we adapt his estimator to our context by looking at the serial correlation of the time component. So we focus on the time component and estimate the variance of that. And so I don't want to go through the details, but the bottom line is that we come up with a formula which is completely data determined. So in principle, a person can pick this as a tuning parameter on their own. We recommend this formula simply because it's data dependent. The user doesn't have to get their fingers dirty with it. And so that's convenience. It's based on in principle, the assumption that the time components follow an AR1 model. And so we just estimate the AR1 component and stick it in. So without going through the details, just we don't think that the choice of this number is incredibly important, but you want it to be in the vicinity of a reasonable number to get a good estimate. Theory. I'll just jump over this, but we have a theorem that says it works. See, there's some math here, but I should have just replied. If the assumption holds, then it works. That's the bottom line. What does it say? It says that our variance estimator normalized by the true variance converges to an identity matrix so that you have consistency, and parameter estimator centered at the true value divided by standard error converges to a normal distribution. And so, and this is with this is the one with the standard error. So what we have a theorem that says that if you do the standard error calculation this way, you have consistent estimates of the variance covariance matrix, and the t ratios are asymptotically normal. And it doesn't tell us, we don't know anything about the rate of convergence.
Also, like, how do you prove this theorem?
How do I prove it? I have a smart co-author. No. How do you prove it? It's a pretty deep theory. What would you?
It is the central limit theorem, right? That the theorem.
Yeah, it's a central limit theorem, but it's a deep theory. So we go back to this basic model, and then there's something called a Hofting decomposition. We take this thing and you project it onto A is the projection of X onto the alphas, B is the projection of X onto the gammas, and that E is the difference. So this is this linear representation is derived theoretically from the nonlinear representation by what's called this Hofting decomposition. And then once you have a Hofting decomposition, then the parameter estimate can be written as a linear sum, where you have a sum across cross-section time series and Socratic, and then you have to work out the variance of each of these components and such. And so it's like there's this interesting theorem that says this is a sample mean. The variance of sample mean has a cross-section component, a time series component, and an idiosyncratic component. And you have to go through lots and lots of algebra. So that's why it's useful to have a co-author who's younger than yourself, because they can actually keep track of everything. Without going through too much details, we have a simulation. And the general thing is when you do econometric theory is the way simulation works is that you do some things, you say you have a model, you do present some numbers, and the end is your method works. Anyway, that's what we do. So we have a model and stuff, and so now we compare a bunch of different methods, and we have these big tables, and you can't read anything. But the bottom line is that these numbers are coverage. These numbers over here, starting here and on, are coverage rates for confidence intervals. So they should be 95%, 0.95 if everything is working well. And our method is the last column. And so what you see is numbers that look kind of like 95% most often. But if you look at, say, Eicher EHW would be doing Eicher Huber right, which would be a very bad idea. And you see some coverage rates which are very far from 90%. One-way clustering also can be very bad. And Kalmer and Gelman, but see, frankly, in this literature, people would not use this. People generally don't use this. What people generally use is Cameron, Gelbach, and Miller. And it's not too bad, their method, but there are cases, like here, 84% coverage and such, where 87, where the coverage is not as good as it should be, and our method does better. It's not perfect, but it moves the coverage rates closer to the dimension. What about what? Yes, we use, sorry. This is Menzel's method. And Menzel's method, we're kind of funny. It has overcoverage in certain regions. This is a Menzel's the bootstrap method. That's what the test is designed to. Nominal means that the theoretical coverage should be 95%. So like critical value 1.96. It's the target. All these numbers should be 95%, but they're not.
So do you assume here that the true number of lags is known to the researcher? And have you explored what happens if you misspecify?
No, we estimate them.
Okay, yeah.
Yeah, so this column, the Thompson's rule uses a uniform weight with m equals 2.
Okay.
So this is Thompson's rule knows that the truth is 2, but our simulation design is not compatible with that, of course.
Yeah.
And you notice that therefore he has coverage rates which can be undercovering. Yeah. Well, yeah. So we just adopted the Sanders rule because we knew it's a data dependent rule that requires relatively little user intervention, and it's very simple. And so we simply adopted it here without any finicking or playing around with it. We did not mess around with that. But you could imagine doing something different. My guess, it won't make huge difference, but
Miller is when we have small number of clusters, right? So we pick up the Cameron-Gelbach-Miller and then do a bootstrap on it. So if you're running into the issue of, a small number of clusters, would we pick up your method and again, then do a bootstrap on that method, like a while bootstrap or something?
Yeah, I would assume that would improve things. I haven't explored that in any way. I mean, in this simulation work, we're playing around with fairly nice context. In fact, you asked the question earlier, if I remember correctly, that what about this jackknife idea? How to apply in this two-way clustering, and the answer is no one's really worked that out. But that's something I've thought about and like to work on. Is how do you extend these jackknife variance estimators to two-way clustering? And so it's not so obvious. It's a simple answer. So there's always room for more work to be done.
Thanks.
Actually, going through one thing is that going through this paper, the asymptotic analysis in algebra is so horrendously obnoxiously complicated that I hesitate to adopt new projects. Yeah.
So if I understand this, maybe I'm wrong. So these are the simulations and the design. When you are saying this is the assumption of the data generating process, that's what it is.
Yeah,
like
yeah.
what? So what are on the rows?
So this is the number of cross sections. This is the number of time series, and then these are weights on the different components. But
No, so
I didn't really describe the DGP because I don't. Yeah.
So what? So 5AR. So that is
that's an autoregressive design.
Yeah, that is you are that if you are assume.
Yeah, and
no, it's okay.
So sorry. That was your question. Yeah.
No,
So here, and this is always important. We're assuming that the time series component follows an autoregression with a coefficient 0.4.
Okay.
Actually, these simulations have all been updated and we've increased it because things get worse when you increase rho. And we also have a design where these things are simple moving averages. So just have very simple time series dependence. Yeah, I mean, one of the questions is what's a reasonable model for all this, and you can, I mean, like after. So this paper was written first before the other paper. Now interested in the question of what if I really move these things around to be more asymmetric, because now I've gotten more interested in this extreme leverage question, and my guess is that these methods won't work as well. And that's, so one of the challenges when you do simulation work in any kind of paper is that the insights you obtain are often limited by the things you explore in the simulation design. So the only way to make that work properly is that the simulation design has to be guided by theory. It has to be guided by your insight of what matters. If you simply say, I'll do 25, 25, you're ignoring the heterogeneity in cluster sizes. You're ignoring this extreme leverage. So you never will learn about it from this simulation design. So you're always limited in simulations by what you choose to do. And so it's helpful to have a theoretical insight to say, oh, I know what's going to make it, this is going to matter. And sometimes you explore that and you find out it doesn't matter. Of course, but anyway.
So in most applied contexts, we have large and small t. And then we're always cautioned about, where the asymptotics are coming from.
Yes.
What's sort of the parallel to that kind of a discussion here? Because you have used them all symmetrically, all your assumptions are symmetric. I mean, you mentioned playing around with them, but
so it really depends on the kind of applications you're looking at. In these, in say classic panels where you have large and small t's, this kind of isn't going to matter too much because this time series dependence is not, it disappears with after a couple of time periods. But the kind of context we were thinking about is these finance applications where these kind of numbers are relevant. And so if you have really a small number, that's the context where I see people using these two-way clustering methods. And, if you had a small number, very small number, like 3 or 4 time periods, our asymptotic theory is just completely irrelevant. The asymptotic theory requires n and t to be large. And to close this out, we have an application. If you're familiar with some basic finance, Fama French have this this 3-factor model of stock returns. And so what you have on the left-hand side is compute the return to an asset. So this is a stock on the left-hand side, centered at the risk-free rate. And then the right-hand side, we have 3 observable factors, which is the return on the market, and then 2 different portfolios, the small versus big portfolio and the high versus low portfolio. If you're not familiar, these are portfolios you can construct from the data. This is things, and this Fama French is a way of pricing stocks. The interest is in these coefficients, and these are widely used in finance. And it's widely understood that this is a two-way clustering context because we have the fact that things are clustered over time, correlated over time, and they and correlated across time for any given, across firms for any given time period, because stock returns move up and down the same time period. And so this is a case where we have 44 industry portfolios, and or we can do individual stocks. And so this is like an example, N is 44,700. And then we have time periods is 100. This is the kind of time periods we're looking at. And we do within transformations and all that. And then just pointing out that when you do that, the things that people are interested in are these betas, the coefficients of, these are just the numbers that come out. And then pointing out that the standard errors matter. This is the I cube right, and then R. So I think the biggest comparison would be between the Cameron-Gellner and our proposal. The standard error does not change, but this one does. So it goes from 4.5 to 5.2, and that is a sizable change in the standard error. And so, and we know like that one doesn't. So there's cases where standard errors don't matter, and there's cases where it does matter. Here, Cameron Gilbach-Miller gives a standard error of 5.3 and we get 7.0. That's a big change. Okay, so and here's a case. Our standard error actually is smaller. So you think generally adding zero correlation increases standard errors. It's not necessarily the case. This case where it actually decreases standard error. And here, these are decreased. So our theory says this should be consistent under a broader range of zero correlation. So we're saying it's better. Look, when you compare standard errors and these are different, it doesn't really prove that these are better. But the fact that they're different simply means that when you report the results, you'll get, it couldn't matter. It couldn't matter. And so that's really the story of that table. I don't want to make too much otherwise of the actual application. And that's really it. More questions? Yeah.
When we're thinking about the difference in difference literature, okay, we know that the staggered difference in difference has its own problems now with the recent work. So we're moving away from the two-way fixed effects in panel studies. So think about the same application in a finance literature, we wouldn't be doing a two-way fixed effects. So one of the solutions proposed by Todd Gormley in an RFS paper or proposed recently by Woolridge is doing these stacked event analysis, right? Like cohort analysis. So instead of having 10 different events where you have staggered events, you stacking them up and treating it as 10 different events, and therefore you'll have cohorts. So there's one firm which is treated, and then you have 5 or 10 firms, which is the control group for that particular treated. And thinking about it, are you thinking about extending this for doing a simulation in those contexts and seeing whether it really matters, because the serial correlation in that case could be slightly lower than what we would have assumed or expected in a standard two-way fixed effects model?
That's a fascinating question. Obviously I haven't thought that. You've done. So yeah, so I said that the standard application I've seen of these two-way clustering is in these finance applications, but I think anytime you have anything like a panel data structure, it's reasonable to think that and the differences can easily get. So yeah, that's fascinating. I think this study of multi-way clustering as such is just isn't really in its infancy, and there's no question that the methods I'm describing here are what we're talking about today, but in 10 years will certainly be eclipsed by something else.
I think there are no more questions, then we can finish this session. Thank you, Professor Hansen, again taking us through this wonderful two-way clustering session. And I would also like to thank us saving us going into all this algebra that probably would have make us sleep, and directly telling us the important results and how those results can matter even if the assumptions are slightly changed in different scenario. So thank you again. And the lunch is waiting for us.
Yeah. I request all the invited guests and guests to conference participants to proceed to the lawn for lunch. Thank you. For the speakers in the contributory sessions, which is going to happen in the other building, we request all of you to reach to your respective room. Please check your program at 1:45 so that the student volunteer can help you to set up the presentations. Yeah, so thank you.